All right, so here we've got our thin film. Okay, so again, this could be air, soap, air, something like that. And what I want to do is I want you to kind of think about some point in space out here, okay, at a location X. Now, if we have a traveling wave, which we do, all right, let's just consider this guy right here. Okay, this guy, we might write that as y is a sine kx minus what's going to the left, so we better put plus omega t plus phi. Okay, just like that. And so if we kind of just think about what's happening with the time portion here, all right, then what that means is the phase, okay, which is, remember, that's like when we start our stopwatch, okay, phases like, and so we've got this guy, of course, this term and this term here are going to tell us about, when our stopwatch starts and stops, okay? And so any two locations near each other are going to be just a little bit different, okay? They're going to be a little bit out of phase with each other, and how much that they're out of phase with each other is going to depend on K and how far apart those two pieces are, okay? Sort of like that. So if they're very far apart, they could be like this. If they're even further apart, we might get something where they're actually back in sync, okay? So our phase could go from nearly zero, okay, something tiny, tiny little difference, to where they're completely out of phase, to they're back in phase again with each other, okay? So that's just a traveling wave, okay? Now, the thing though about this first reflection, okay, the white one that I've done there, so this guy here, I'm trying to highlight it a little bit more for you, okay? It's a reflection, and the wave had to slow down. And whenever the wave slows down, then that means there's an inversion, and the phase change is 180 degrees or pi radians, okay? Just like that. So if I want to compare the wave of incoming, to the wave outgoing on the reflection, then the phase difference between those is this right here, kx plus pi, all right? Sort of like that. Okay, now let's take those off of there. Okay. Now, I want to play the same game, thinking about the phase for the other one. All right. And the other one, I mean this guy. Okay. It's coming all the way from over here. And remember, it actually went all the way over, and now it's coming back. Just like that. Okay. So I'm going to get, I have the possibility of a phase change because of my reflection, and then I'm going to have some kind of phase change, which is going to go K and my delta X. All right, K and my delta X there. Now, in this case, K on the inside is different than K on the outside. This is actually K sub n. All right, so it's going to be different because the speed of the wave is different, okay? And my delta X, my green's not showing up as well as I'd hoped, is 2t. Because I got to go all the way across and I got to come all the way back, all right? And so the phase difference caused by going across and coming back is given by this term here, all right? So both of them share. Once we get back on the front side, okay, they both share this part, but they're different with this other term on here, okay? So those two waves, so that term, the difference between pi and 2k and t, that's what's going to determine if the two waves are going to be like this, or like this, or like this. Okay? You may need to rewatch that. That's a little bit tricky. Okay, that's a little bit tricky, but I'm just basically trying to figure out where's my phase. If I pick some arbitrary location out here, what phase is that going to be? Okay, so we got the phase from the outer reflection and then the phase from the inner reflection. Okay, so what we're going to do now is we're going to subtract those. Okay, so here we are. Outer reflection, inner reflection. Okay, so the outer reflection is this guy. Oh, I should try to use the same colors. So here's the outer reflection, like that. And then this is the reflection off the inside, like that. Okay, so that's the one that's come all the way like this. All right, now if we subtract those, well, it looks like we're going to subtract them, but I want you to look at K in first. All right, so K is always 2 pi over the wavelength, but our wavelength is going to be different because of the index of refraction there. So little n there is the index of refraction. Okay, now remember, it's kind of weird if we have a larger index of refraction. That actually means it's going slower. Okay, and you can see there that the slower we go, as n gets bigger, then my wavelength has to get smaller. So this is the marching band taking smaller steps. Okay, kind of like that. And what that does to us is it modifies, so we get K sub n here. Now I've got K sub n as a function of my index of refraction and my wavelength. Okay, wavelength in a vacuum there. And the result of all that is that my inside phase turns into this stuff here. So it's starting to look kind of complicated. All right. It's going to get a little bit worse. So hang in there. All right. And when we get to the end, I'll let you know. Okay. Now, I think on the next slide, now we're going to subtract these things. Yeah, there we go. Okay. So here is on the outside. Okay, so that is this guy. And then here is the secondary reflection. I call it inside, and it's here. And now look what happens once we subtract these things. Okay, when we subtract them, we have this interesting relationship. Okay, just like that. Now, that's the part that's really good to determine when we talk about interference. Remember we said there's a whole range of things. We've got constructive on one side and destructive on the other. There's a whole range, okay? So what we want to know is, when does this delta phi value here create constructive interference? When does it create destructive interference? Well, it creates constructive interference whenever delta phi equals 2n pi. Now, capital N is a counter, all right? So in other words, if delta phi equals 0 pi, or 2 pi, or 4 pi, 6 pi, 8 pi, okay? Whenever that condition is true, then we're going to get constructive interference, which means on the outside, the waves will be like together. Okay. However, if delta phi is an odd number of pi, okay, so if it's pi, 3 pi, 5 pi, 7 pi, 19 pi, okay, then when the secondary wave pops out, the reflection in the secondary wave will be out of sync, okay, and we'll get destructive interference, okay, we'll get destructive interference. All right, so are the two waves going to be synchronized or completely unsynchronized? Okay, constructive or destructive. And all that's going to depend on the index of refraction, the thickness, and the wavelength itself. Okay. So what I've done here is here is that relationship I just had. Let me go back so you can see for sure. Okay, so this equation right here for the delta phi, that's this right here, okay? And this condition here is when we get destructive interference. On the other hand, if I take all this stuff, which we just had for our delta phi, and set it equal here, 2n pi, then we get constructive. All right, so I'm trying to come up with a way to relate n lambda and t, n lambda and t, all right, to find out, are we going to get constructive or destructive? So those two conditions, if we solve for t, okay, what we're going to end up getting is for destructive interference, if we solve for t, we have this relationship. It simplifies a lot, okay? On the other hand, if we are interested in when do we get constructive interference, then it simplifies to this condition here, all right? And you can see that they are very similar. They're pretty much the same here and here, okay? The thing that's different is in one case we've got n, in the other case we have n plus a half. Okay, and that kind of gets back to what we were talking about, path differences earlier. Okay, so destructive, that's our condition, and constructive, that's our condition there. All right, n is a counter. Okay, so n is going to be 1, 2, 3, 4, 5, whatever. Now, most of the time, what we're interested in is we're interested in knowing what's the minimum thickness for a film. Okay, what's the minimum thickness? And so a lot of times, I'm not going to say every single time, but most of the time, you're going to just let capital N be 1. Okay, now that isn't always the case. All right. You might have a case where it says, hey, you're getting destructive interference. How many wavelengths did it go through? Okay, which means what's capital N? All right, in that case, what you're going to do is you're going to say, you're going to say T divided by lambda 0 over 2n is equal to some number n. Okay. And then you do that calculation and, n maybe turns out to be 12. Great. So, it's 12 wavelengths across there. Okay. Or the question might be, hey, the film is such and such a thickness and the wavelength of light is such and such. Are you going to get constructive or destructive interference? Okay. You do this same calculation here, and then you look and you see, what does n turn out to be? And if n turns out to be a whole number like 7, then it will give you destructive interference. Okay. On the other hand, if it gives you 7.5, then you're going to have constructive interference. All right. So there's several different ways to kind of look at that, but they all come down to the same basic idea. All right. So let's take a look at these soap films. All right, so the top two pictures are bubbles and the bottom one is about to be a bubble. All right, so in the picture up here on the top left, right up here, you see all those swirls and stuff. And if you've ever been able to watch a soap bubble carefully, okay, when you can see these colors, all right, they actually kind of swirl around a lot. And if you had the chance to look closely, then you'd see something that looks like this, okay? And every one of those colors, just like with when I was talking about the gasoline on the water or an oil slick or something like that, those different colors represent different thicknesses, okay? And oftentimes you see things like this where there's a pattern. Purple, blue, light purple, yellow here. And then that pattern repeats. Purple, light blue, and then that pattern repeats again. Okay. And what's happening in that case is for all these first set of colors, N is 1. Okay. All right. But then the film gets a little bit thicker, and the second time around for all these, N is 2. Okay. And if the colors kept going, then you'd get N equals 3. Okay. So my film is gradually getting thicker. Okay. So let me kind of try to draw it over here. So we might see, I'm just going to draw it in a straight line here, but imagine something like this. All right. It's getting thicker and thicker and thicker. And so I'm going to have, my yellow in here. That's this here. And then a little bit later, I can get constructive interference with yellow again. And then a little bit later, I can get constructive interference with yellow again. All right. Maybe over here is where I get blue. Here I can get blue again. Here I can get blue again. All right. And again, these are going to be regions where N is 1. All right. So it's real short. Boom, boom. Over here, it's going to be regions where N is 2. So it's going to go boom, 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 a little bit further and come back. And over here, N is 3. So a little bit further it comes back. Okay. But in all those cases, we're getting constructive interference out on the other side. Okay. Now, if you have a little wand and you're going to blow some soap bubbles, okay, if you look at it carefully, then you're going to see this repeating pattern, same sort of thing here, okay? So, and then it repeats, and it repeats, and then it repeats. And it's the same kind of thing. And it's going to be 1, 2, 3, 4, sort of like that, okay? There is a point, all this region up here, where the film is too thin and we don't get any constructive interference, okay? It's so thin. And as you hold the little wand there, you're going to see these bands of colors change, all right? They're going to kind of appear to move because the liquid is draining out. And as the liquid drains out of your magic wand, it gets thinner and thinner and thinner. And that causes these things to change, okay? Now, they have to get kind of thin before you can see these colors, all right? We call it thin film, all right? If the film is too thick, then there's a second thing that starts to happen, and that second thing can obliterate everything we've been talking about, okay? So this is a model, and it's only applicable in certain situations. And those situations are where it's really thin, okay? So, if you're just looking through a piece of glass, you don't see those rainbow colors like that, okay? That doesn't happen, all right? And that other effect has to do with what we call coherence and decoherence, all right? And that's a little outside of the scope of our course, but that's why you only see this if the thing you're looking at is very thin. The idea of coherence, basically, imagine the marching band, okay? Suppose the marching band going down the street, instead of being a block long, what if it was 10 miles long? Okay, if that block is 10 miles long, the chances that the people in the front are synchronized with the people in the back begin to become extremely small. And so coherence and decoherence kind of begins to talk about things like that. So if the band members start to get out of sync with each other just because they're so far away, then you're not going to get the destructive or destructive, okay? But as long as your marching band's only a block long or something, you still have good coherence, and you're going to get good constructive or destructive interference as the situation happens. Okay. All right. So this is the end of part 2. We're going to do one more video for you. We're about to wrap it up here. Okay. Because we have another situation. All right. So this situation here is, I like to think of it as a sandwich. We've got something, something, and a whole different thing in the middle. Okay, so it could be like air, and a soap film. Or it could be a piece of glass, and a little bit of air in between them. Okay, sort of like that. But it's like a sandwich situation. Now, the oil spill and the peacock feathers are a little bit different. So we're going to get into those in the next video.